Okay, we're getting close to the end. We have week 11 and week 12 to go. And we believe week 11 is pretty good. People have been clamoring for applications of linear algebra. And this week we will start off with just that. What we're going to look at is how projection onto the column space of a matrix can be used to do data compression. Now, for the most part, what we're going to show is not really a practical algorithm. We will touch on a practical algorithm based on the singular value decomposition very briefly at the end of this week. But the example that we pick will give you an idea of how linear algebra can be used. It will also help you understand the mathematics behind the topic, and that's our primary concern. So let's see what low-rank approximation is all about. Well, here's a picture that you've seen a few times during the course. It's the banner for LAF, Linear Algebra Foundations to Frontiers. And the yellow line there is meant to signify that one can think of this picture as a two-dimensional matrix, where each pixel is an entry in the matrix with some value. And the yellow line there then represents a column in that matrix. Given a vector A, we saw that one can take any other vector, B in this case, and project it onto the space spanned by A. And notice that then the projection, which is an orthogonal projection, because this angle here is a right angle, this orthogonal projection is just a multiple of vector A. And that then creates a vector u orthogonal to vector v such that b is equal to u plus v. Now, how can we use this to do data compression? Well, if we take each column in a picture, and you don't know yet what picture this is, if you take each column in a picture and you project it onto one of the columns of that picture, in this particular case, I took the first column of the picture to be the vector onto which we project. And we do this for each of the vectors. And we then take the vectors that come out of this projection and make it back into a matrix. Then this is the picture that you get. Now, we could take two columns. So in this particular case, I took two columns of our banner. The first column here and some column in the middle. And we took those and made them into the columns of a matrix. And then we did a projection of vector B onto the space spanned by the columns of A, which means that we take this projection to be a linear combination of the first column of the banner and a column in the middle of the banner. And then we repeat that for each of the columns, and we put it back together as a picture. And for the picture with which I started, the mystery picture, this is what you get. You're starting to see some detail, but I suspect that without knowing what picture this is, you have no idea what you're looking at here. So let's do the same thing, but let's now take 5 equally spaced columns. Notice that that simply means that we now have 5 columns in our matrix A. We again project onto the column space of that matrix. And then we use that as our approximation, and we repeat that process for each of the columns. And this is what we get. Now, if you've paid attention in this class, you might actually be able to guess what this is a picture of. But to really see what's going on, you need some more. This is what happens if you take 10 columns equally spaced. And I suspect that those of you who paid attention to the emails that we've been sending out will start recognizing this as this building that shows up in the lower left corner of each email. And what it is our beautiful new computer science building at the University of Texas. It's the Gates-Dell complex. And this is actually the picture with which we started. So here's the original picture. And here is an approximation when we only use 25 columns for our matrix A. During the first few units of this week, we look at the math behind this example.